Good afternoon. How are you guys? We are team 19, and we're presenting our senior design project. It is the ROARsat for NASA's FUNsat competition. The group consists of Sergio Hernandez, Walter Salas, Cruz, Philippe. Our advisor is Sabri, Dr. Sabri Tosunoglu, and our mentor is Philippe. So, FIU's Pico satellite is our ROARsat. This is going to be for, like I said, a NASA's FUNsat competition, which FIU has competed for before. Now, FIU has not successfully been top 3 during this competition. Hopefully, by senior 2, we can make it to the top 3. And if we do successfully, NASA will give us all certificates with signed by boards, and our name will be on the website. We'll be recognized for the next 2 to 4 years. So for the NASA competition, it all began in 2004. It's here in Florida, in Cape Canaveral. And any Florida university can take place in this competition. And we have a couple of restrictions that we have to go by. So some requirements for the competition, in our case, is has to be 10 centimeters by 10 centimeters by 30 centimeters. It also has to be a maximum mass of 8 kilograms. If we do get to launch it, it'll go up for a lifespan of 6 months, and it has to go up to the exosphere, which is, like I said here, 600 to 700 kilometers above the Earth. This is an image of our prototype. So on the outside, it's going to look like this, and inside, the reason you see those plates in there is because we have components in there, like a power source. This is an interdisciplinary project, so we have to worry about the electrical side of the satellite, the programming side of the satellite, and also the mechanical side. We have to worry about attitude control, make sure the satellite doesn't lose its center of mass and start rotating on its own. So our power sources and sensors and communications will be in those levels. So PicoSat background, the reason why they've become such a big deal lately is because the United States Department of Defense, they're now interested in this, and NASA has been also looking at this. They're very cost efficient. You know, this cost a couple of grand, $2,000, $3,000. Anybody can make it, and compared to NASA's massive satellites that can cost up to millions of dollars, a lot of research behind it, and if anything goes wrong, much more monetary value is put into that. And also there's a big worry of the space congestion. There's a lot of orbit, there's a lot of satellites in orbit. Now it's 2015. This began since the 50s, so there's been a lot of satellites being launched, and now it's a worry that we're getting congestion with satellites. Now, some mission objectives will be presented by Walter.
Correct. So as for mission objective for the satellite, we're mainly trying to concentrate our research on weather conditions. We know global warming is affecting all of us at this moment, so pretty much that's the reason why Sergio was explaining our satellite is divided in 3 parts. That's what we have planned so far. And also in the bottom part, we're going to include cameras, which is our mainly component. We're going to be able to take pictures, not only video, but we'll also analyze pictures, and we're planning on doing some thermal studies. That's why we have these pictures, so we can study patterns, study weather conditions in general, and also study level rise in different locations. Now the benefit is that we have a GPS tracking device, so the satellite can work anywhere in the world. As far as we can reach a satellite, it's going to be able to be controlled. As a global impact, the benefit of this project with people is that we're going to gather the information and be able to expand it. It's going to be at a low cost. It's going to be available for everybody on the internet. Pretty much everybody that study weather conditions or different studies are going to be able to get into the information at a much lower price than NASA have their own studies. Also, the materials that we're using for the satellite are very recyclable. If at any point we need to like upgrade the satellite, we can just bring it back and modify it since everything is it's capable of being upgraded. Now this is a budget that we have so far. We've been doing the research, and for the optical part we have two cameras that are going to be doing photos and videos. We're trying to incorporate a third camera which is going to be doing the thermal studies. For the power system, we have our batteries, which is in a cost efficient way. It's only $150 for batteries and mainly for solar panels that we're trying to incorporate in the future. For the communication system, we have 2 boards, and they are going to be able to communicate with the satellite on ground. Attitude control mainly is just to have the satellite pointing in the right direction and be able to take pictures as we need. For miscellaneous, we have $500, which are going to be for everything in general, but that's our estimate so far, 1,700. And now my partner is going to talk about the time and the
Alright, so a big part of this project isn't only trying to work in an interdisciplinary field, it's also trying to understand how teams work in the real world. So how we have our goals allocated is, up until now, we've been mainly focused on understanding the research and the history of satellites and what has been done so far in the FUNsat competition, so we know how we can set ourselves apart. In the upcoming months, we're going to focus more on the actual manufacturing part of it, along with some simulation and testing. That way, by the time the competition comes around in March, in April actually, we should have everything completed. And the way we split up the responsibilities to allow for an efficient workforce is that Sergio will be in control of the optics and the attitude control, which, as Walter stated, was to control the rotation of the satellite and its location, along with the detailed pictures that we need to achieve all of our goals. I will be more focused on the communication subsystem, which kind of dictates how the satellite communicates with the ground station and so forth, along with the power subsystem, which is the batteries and the solar panels, and Walter will be more focused on the simulations in MATLAB, with all of us playing a role in the actual manufacturing of the satellite. So some considerations that we know that we're going to need for sure is insulation, right? Because the satellite's going to be up in the exosphere, so it's going to be exposed to radiation. To ensure that the inner components are working as needed, there's going to be required insulation to keep the internal temperature at its desired level. Some that we've looked at so far is styrofoam and aerogel and Kaplan tape. We're leaning towards aerogel because it's proving to have the highest thermal conductivity and also to be cost efficient. Also, since the satellite's going to be rotating in space, not all the sides are going to be facing or exposed to sunlight. So we need to find a way to allow for the solar panels to keep the internal components charged when we need to, in spite of this fact, along with MATLAB simulation and motion analysis to ensure the attitude control. And then, since we're dealing with the satellite and with communication, there are many standards that already exist due to the vastness of this project. Here we have listed some specific standards. There are many, many more than this, but the overall gist is that a problem with small satellites is space debris. So a lot of these standards are going to mitigate space debris and also to ensure that satellites aren't really colliding with each other and that when they're returning, they're not really burning up. So most of these standards are placed to ensure the overall safety within having a satellite in space. And these are just some of our references, and that's it for our project. So any questions?
I have a few questions, but first, it's nice that you put the references there, citing where you got your work from. First, does NASA want this to be retrievable, or after 6 months, just let it fall out of orbit?
Yeah, we believe we don't know yet for sure. We haven't done as much research to look into that part, but we believe it's going to be retrievable yet. They're also in charge of the launch. We don't take care of the launch. So what happens is we have to send a written proposal, and if they like it, if we're good enough and make top 3, then we get lucky and they launch it for us. If we don't make it top 3, we don't even get considered to be launched.
Okay. My second question is, have you reviewed the standards?
There's a lot of them with satellites. Some of the ones we listed up there, some of them we've reviewed, but the overall gist behind them is what I stated. They're mainly focused with space congestion and safety within having that many satellites up in space.
Yeah, as far as NASA, we don't have many restrictions. It's basically online information that we get.
So a lot of like space law and internal and national laws that we have to abide by for satellites.
All right. And my last question is, what are you using for your attitude control?
For simulation-wise, we're gonna be using MATLAB, but that's part of the future work that we have to look into. We don't know what we're gonna use exactly to keep it in place.
We know we want to have a Beagle board up there along with several other, like an Arduino, that we can have certain programming intact to allow for us to have better control of the satellite. But as far as the actual attitude control, we don't have any right now yet.
Right, because most of the bigger satellites use thrusters to get that satellite into position.
But for a satellite, we decide.
Yeah.
Yeah, so far we were researching and we have different options. There are mainly like small parachutes where they are able to rotate and move according to the air.
What the previous one that FIU has done before, they did a CubeSat and they had a glider and then a little motor attached under the glider, and then that motor would move, and that would help the satellite move and stay in place.
Thank you.
So do you do a lot of simulation work on this design?
Yeah, we're doing the simulation. We haven't finished with everything. Mainly we're trying to concentrate on bending, what happens when it's coming back from space, if it's going to be able to handle any collisions.
The other question I ask is actually getting into space, is taking that initial acceleration.
Yeah, the vibration from the actual rocket, we also have to do analysis on that too. That's one of the considerations we have to make along with the thermal analysis. Because it's also going to be stacked with the other satellites that they're sending in the rocket. So we also have to take into account the mass from the other satellites along with the vibration.
Oh, so it's even more complicated.
Yeah.
Do they give you the geometrics of what all the other satellites can look like so that you can model around it?
Oh, it's just the standards. Like we have the maximum mass along with the dimensions of the satellites.
I think we can be sent up either with the standards that's like ours, the 10 centimeters by 10 centimeters by 30, or a CubeSat, which are 10 by 10 by 10 centimeters. They're both able to.
But are you doing vibration analysis, for example?
Yeah, we're gonna have to.
You're going to have to do some vibration
Yeah.
analysis. Yeah, obviously you need the stress analysis.
Yeah.
All of the electrical systems, are they designed, I mean, are there restrictions on them to ensure that they won't get destroyed?
I mean, with the vibrations themselves.
Yeah.
Well, that's part of the analysis that we have to
Yeah,
do.
we have to put something inside so that nothing gets loose, especially on the launch, which is where
Oh, I know.
most of the vibration comes from. So yeah, we're analyzing and researching on what we need to put in order for nothing to get loose.
Keep it compact.
That's our main problem right now because up there's not much movement.
Right, once you get there,
That's fine.
you're pretty benign, but getting there is the story.
Correct,
Yeah.
correct. And that's gonna be determined by NASA because we don't do the launch. They're the ones who.
But you do design what's in the
Correct,
box
right.
to be able to survive the launch.
Yes, we have to worry about it.
The box will have to survive the stresses,
Yes.
acceleration, vibrations,
Yes.
thermal analysis will be needed.
Thermal
I mean, there's a lot of analysis we need to do
Mhm.
before saying that this box is gonna be safe,
Yeah, it's a lot of
Mhm.
simulations.
you know, so.
And we're also even considering conducting a test by sending it up with one of the balloons to make sure all the actual components work when it's like at a distance.
In order to get
Yeah.
testing and make sure that the electrical components work and the Arduino, like Cruz said, we're gonna hopefully do a balloon launch, and attach it to the satellite and send it up to about 50,000 feet and see if we can get temperatures and stuff.
Where do you do that work?
We're planning on doing it somewhere in the middle of the US where we have enough land in case when it comes down it's gonna. We've seen
Yeah, so far
videos
we-
already on
yeah.
YouTube, and when it comes back down, they have to drive 200 plus miles to find their satellite.
Would you put all your work on the line? What if the balloon pops?
Yeah, that's
satellite,
Everything disappears.
everything.
No, that's the idea. There's a
Could happen
company
very
that
easily.
we research and there's a company that creates the balloon especially for the altitude that you desire. So we're trying to get as much information as we can in order to be successful competition. So mainly the purpose of that is to test that everything works at a certain temperature, especially for.
But we have thought about.
NASA's probably got some nice freezers and nice ovens to test
Sure.
thermal
Oh, yeah.
samples.
That too, but so far we research on that.
Yeah, we'll look into it too. Test
And
those.
simulation tools too. They should have, excellent simulation.
I have one last question.
Yeah.
You have on your schedule that you're finalizing your design at the same time that your competition starts.
Yes.
Yeah.
Right. So you might want to
Finish
consider
it.
finishing your.
Well, ideally, we'd like to finish it by March, but we know how things work out, so I'm sure like during April, we'd still be like fine tuning some things,
Right, but your schedule says up till May, you're gonna be completing your design, but your competition starts in April.
Yeah, yeah. Yeah, we'll try to push it along. This is worst case scenario.
I have a few questions. First of all, going back to your first slide, that's just, go back to your first slide, it's just a point of clarification. Next one. Right, that's one. So dimensions must be within maximum length of 10 centimeters by 10 centimeters by 30 centimeters. I'm not sure that's what you exactly meant. The length is
It's
10
not the main-
centimeters,
yeah.
the width is what, 10 centimeters, and the height is 30 centimeters,
Yes, yes, yes.
right?
Yes,
Right.
yes, yes.
So you need to be more clear as far as that's
Just
concerned.
saying length, right, yeah,
Right.
yeah.
So,
Yeah, that's a mistake.
kind of
that
fix
one.
that.
Right.
now also, when you go back to your cost, something you mentioned, you said you're gonna have what, 2 cameras
Yeah,
at $600, and then you're thinking of a third camera,
correct.
how much, that'd be what, another $200 maybe?
The cameras, basically
$300?
for the video, we research and it's around $80. It's not really that expensive. The high definition camera, it's around $200, and the thermal camera is around $200 to $300.
Oh, so you may get the 3 cameras with the $600.
Correct.
Okay. Okay. That wasn't clear. I thought you were going to get 2 cameras at $600 and you're thinking of a third
We're
one.
already researching.
Right.
Okay, all right. Something that Cruz said, you started to mention about multidisciplinary field or trying to get a challenge should be
Well,
getting.
that, and some of the benefits of this project is that it's interdisciplinary. Like, we're not only working on
And how are you going to try to get, how are you going to try to get that multidisciplinary thing into your project? Are you going to do anything specific to make sure that it's, that it is multidisciplinary?
Well, there are many components to it. There's an electrode component to it, there's power, there's programming that we actually have to do with all the boards. There's the all mechanical analysis that has to be done to ensure it's working.
And are you going to get some help, someone who?
Yeah, we have our
that-
mentor, Pradeep Shindi, who's pretty knowledgeable in these fields, who actually participated in the previous.
He's a PhD student in mechanical engineering,
Mhm.
and he did work in this project before, as well as Shell electric car design. He's very interested in these projects before,
And
so
he's going to help as far as
he
the
will, yeah,
electrical part is
that
concerned.
helps.
But you're going to go beyond electrical. You mentioned, you started to say something beyond electrical. What else?
Oh no, I said there's an electrical component, there's actually programming, computer programming that has to be done.
Mhm.
There's a mechanical analysis that has to be done.
Mhm.
It's a satellite, so it's an aerospace project, so it covers a lot of the engineering disciplines.
Any comments?
Actually, one comment.
Yeah, go
Look into gyroscopes, what they use for the control instruments on airplanes. Maybe you can adapt the gyroscope they use to control your attitude. Just
Okay, thank you.
thinking.